Hello again. This is then what I said in the previous video is going to be part 2 of differentiation of exponential and log functions. So in part 2 of differentiation of exponential and log functions, we are going to look specifically at the derivative of the log function. Now, when I talk about the log function in AP mathematics, you always have to go and accept that we're going to talk about the derivative of the ln of x. Because as we said, my natural logarithm is not actually log base 10x, it's actually log base ex. So because ln of x is log base ex, we are going to look at the derivative of that log base ex function, or the ln of x function. Now, in order to know what the derivative of that log function is, we're going to quickly have to go and just use our inverses. So by the way, this deduction that I'm going to show you just now is not part of the syllabus, meaning you don't have to be able to prove this. It's just useful to understand where the derivative of the log function comes from. So I'm just going to show you where the derivative of the log function comes from, but again, like I stated, you don't have to be able to do this little proof that I'm going to do over here right now. It's just for interest's sake. So the first thing we do is we go and we write this in exponential form. So if I write this in exponential form, I'm going to go and say e to the power of y is equal to x. So e to the power of y is equal to x. And that's just using my definition of a logarithm, where I can change it from logarithmic form into my exponential form. Now what we're going to do is we're going to find the derivative of this particular function. But in order to find the derivative, I'm just going to write in standard form, x is equal to e to the power of y. You need to realize that y is not the independent variable, and y is the independent variable. It's no longer the dependent variable, and x is no longer the independent variable. It's now the dependent variable. So there, because x is the subject of my formula, I can't find dy over dx. I have to find dx over dy. So I'm finding the derivative of the function x in terms of its independent variable y. So it's dx over dy because it's written in that format. Now, we specifically learned that if I find the derivative of e to the power of y, then this is just going to be e to the power of y. Now, the good news here is the following. Normally, y would be a function. So normally, we would go and have to find the derivative of y. But remember, we are not looking at dy over dx. X in this case is the function, y is just my independent variable. So that is why the derivative of this is simply just e to the power of y. Okay, so I'm done here. Now, logically speaking, we do not want dx over dy. We want dy over dx. So I'm going to change that to its reciprocal. And because it's an equation, please guys remember, if I do something on the one side of an equation, I have to do the same thing on the other side. So because I have dy over dx there, I'm going to write 1 over e to the power of y over there. Now, please remember, people, we said up top over here, y is equal to log ex. So I can now go and I can make a substitution saying that y is equal to log ex. So dy over dx is then equal to 1 over e to the power of log ex. Now, I don't know if you remember, but when we were doing the laws of logarithms, so my logarithmic laws, we said there were 4 logarithmic laws, but then we also did a couple of deductions from the 4th law. And one of the deductions from the 4th law, if you go and look back at the previous video or the previous notes, you will realize that when I have a base log with that same base x, I know this is just equal to x. So that whole thing right there is just going to be equal to x. And as I said, this is one of my deductions from the log laws that was discussed in the previous video. So if this doesn't make any sense, please go and look at the notes or go and look at the video. By the way, when I say the previous video, I don't mean part 1 of this. I'm specifically referring to the video on the number e and the logarithmic function. That's the one I'm referring to, where you get that lovely deduction. So that actually means then that dy over dx is 1 over x. So we are saying the derivative of the log with base e, in other words, the derivative of ln x, is 1 over x. And I'm going to show that to you over here on your formula sheet. right there. The function is ln x, the derivative is 1 over x. So yes, it is on your information sheet. This was just pretty much to show you where that derivative comes from. Now, just like we did for e to the power of x, we also quickly have to talk about this one, the function of a function rule, meaning I'm not always going to get the ln of x. Sometimes I'm going to get the ln of fx, so there will be an inside function again, just like with e to the power of x. And then what I have to do is I have to say dy over dx is then going to be equal to, and now watch carefully, because the outside function in this case is that log e. And we've just established that the derivative of log e x or ln x is 1 over x. So now you have to be careful, because now what you have to say is you have to say it's 1 over that particular function, which is the ln of fx. Oh, sorry. Not the ln of fx, the ln, it's just fx. Because remember, and I'm going to state this again just to make sure you understand it properly. It's over here. We are saying the ln of x is 1 over x. And because the ln of x is 1 over x, it just means whatever is inside that logarithm, it's just going to be 1 over that function. And that is why over here as well, and I'll just clean this up, because I'm having a glorious day with all of these lovely mistakes. Hopefully you'll forgive me for this one. So that pretty much also just says, when I find the derivative of that ln of fx, then just like with this one, where x then just goes into the denominator position, I also have the same situation where I have 1 over fx. But now you have to remember very, very carefully. We said the inside function is fx. And if I say the inside function is fx, I need to follow the chain rule, which means I need to find the derivative of that fx to multiply. And that is why when I tidy this up, I will find my derivative is the derivative of that inside function divided by the inside function. So I know this is a little bit awkward and this is a little bit strange, and it's going to take you a little while to get used to it. And the other problem is this is not on my formula sheet. So if you see this, they give you the ln of x as 1 over x, but they do not give you the ln of fx. So this is one of those things that you are going to have to memorize, in my personal opinion, because it's the only way you're going to be able to do the next couple of examples. And also, when we start doing the integration of functions later on, then you do need to know this one. You really, really, really need to know this one. So again, I just want to state, if I have the ln of a function that is not just x, so it's not just x. If it is just x, I can go back up top here and I can say the derivative of the ln of x is 1 over x. That's easy, simple, and straightforward. But the moment there's something other than just x in there, you're going to say it's the derivative of that inside function over the inside function. So that deduction, very important. Right, so again, I'm going to write this down. Like I said, this one is on the information sheet, like I've shown you. So on the information sheet, you've got this one. This one, however, is not on the information sheet. So this one, please, I would memorize this one if I were you. We've just discussed it. It's going to be the derivative of the inside function divided by that inside function. So whatever I have inside that ln, you're just going to say the denominator stays exactly the same, but the numerator is the derivative of that function. So this one, please, people, I would memorize this. I cannot state how important this is enough. Please, 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 please memorize that. Okay, so let's get started on the examples. We have some examples on page 74 and 75 of the textbook. So the first one, they say differentiate the function ln of x squared minus 3x plus 1. So this one specifically is one of those ones where my inside function is not just x. So because my inside function is not just x, I'm going to use this particular deduction that I've already discussed with you guys. So let's just watch our notation. I'm going to say d over dx of that function. And the reason I use this specifically has to do with the fact that they didn't define this as y, they didn't define this as fx. So because it wasn't defined as something specific, I needed just to go and say it's the derivative of that function with regards to x, which in this case is my independent variable. So using this particular one, we then just go and say, okay, so the derivative of ln of a function is then going to be the derivative of the inside of the function, so the derivative of that. So that's going to be 2x minus 3 over whatever that function is, x squared minus 3x plus 1. And again, I know this is a little bit strange, and I know this is going to take you a little while to get used to it, but please, please, please go and practice. The more of these you do, the easier it becomes. Okay, the next example, number 2, says if y is equal to the ln of x plus 1 over 3x minus 4, find dy over dx, so find the derivative of that particular function. Now you'll see here, I put a little note there. Sometimes the log laws is the easiest thing to do, meaning I need to go and first simplify this algebraically before I attempt to find dy over dx, because it just makes everything so much easier. It's very, very tricky if you want to go and find the ln of a function divided by a function, because, oh my goodness gracious, this is going to be horrible. It's going to involve the quotient rule. So because it involves the quotient rule, it's just easier to use the log laws. So please note this is still y. I'm now just using the log laws to expand this. So in the video when we discussed e to the power of x and when we discussed the log laws, we said if I have a single log where I divide two values or functions or whatever, then I'm going to go and make it into two logarithms with the same base. So this is ln, where I take that x plus 1 and division becomes subtraction, so minus the ln of 3x minus 4. So I've just used the log laws, and this is specifically that subtraction law, but I use it in reverse to expand. Because now I can again go back to this little deduction over there, where I say I can now go and separately find the derivative of these two, saying the derivative of that particular one is going to be the derivative of the inside function divided by that function minus the derivative of that inside function divided by that function. So I can now write dy over dx because I'm ready to find my derivative. So dy over dx is equal to the derivative of the inside function, which is 1 over x plus 1, minus the derivative of the inside function, 3 over 3x minus 4. Much, much easier than attempting to use the quotient rule there. So please, people, if you can simplify your expression using the log laws, please do so first before you go and find the derivative. Otherwise, you're going to end up with a very, very complicated derivative, which is definitely not worth it. Okay. Right. So, next example, 3. So, 3 says, find the gradient of the normal to the curve. Now, please be careful with that one, because they are not asking for the gradient of the tangent, they're asking for the gradient of the normal. Now, I'm not exactly sure if we have discussed this before, but I'm going to just mention it to you guys again. The normal to the curve does not have the same gradient as the curve. The normal to the curve is perpendicular to the curve. So let me just write that. The normal is perpendicular to the curve at that point. So we are going to find the gradient of the tangent, but after we find the gradient of the tangent, we're then going to change that into the gradient of a perpendicular line, because please remember the normal is perpendicular to the curve, whereas the tangent has the same gradient as the curve. So you'll see just now later on we're going to change that. Right, now if I want to find gradients, please remember guys, gradients is all about derivatives. So whenever they ask for a gradient, they're asking for the derivative. You don't even have to question it. So because we're asking for the gradient of a curve, we need to find the derivative, which is the gradient function. So in order to do that, I'm going to go and say dy over dx is then equal to, and this is again just the ln of an inside function. So if you recall, the ln of an inside function is going to be the derivative of the inside function, which is 3x squared divided by that inside function, so x cubed minus 5. Okay, now I'm first going to go and I'm going to find the gradient of the tangent, because the gradient of the tangent has got exactly the same gradient as the curve at the point where x is equal to 2. So the gradient of the tangent, I just have to substitute 2 into x go. And that's going to be 3 times 4, which is 12, over 8 minus 5, which is 3, which means the gradient of the tangent is 4. But, like I said, I do not want the gradient of the tangent. I want the gradient of the normal, and the normal is perpendicular to the curve. So that means the gradient of the normal is then going to be equal to the negative reciprocal, which is minus 1 over 4. And that is the correct answer according to the textbook. I'm trying to keep myself honest. I'm checking the answer in the textbook. If I do make a mistake, I will go back and correct it. So if you have spotted a mistake and you're going like, ma'am, Jared, that's absolutely fine. You can keep on doing that. Hopefully I will correct the mistakes before they become fixed for posterity forever and ever and ever. Let's hope they don't. If they do, you can always blackmail me from now to infinity. Right, so let's continue. Differentiate the following. Now you'll see these ones, when they ask for the derivative of these ones, these could be possible combinations of e and of that logarithmic function. So now you have to concentrate quite well. If you look at this one specifically, you'll see I've got y is equal to e to the power of x times the ln of 2x minus 1. Now, this is very importantly a product rule. So I've got a product rule where I've got this function right there multiplied by that function right there. So that's product rule. Because there's the multiplication of the two functions. And over here, I've got that chain rule, that deduction. So that's that chain rule deduction that I showed you guys, which I told you, please, people, memorize that the ln of an inside function is the derivative of the inside function divided by the function itself. Okay, so using the product rule, I go dy over dx. So according to the product rule, I first have to find the derivative of e to the power of x, which, lucky for me, is just e to the power of x. So that's the derivative of the first function multiplied by the second function. And I'm not touching the second function at all. Plus, now comes the tricky part, because now I have to multiply the derivative of that function where I use the chain rule with that deduction that I showed you, 2, which is the derivative of 2x minus 1, over 2x minus 1. So that's the derivative of that function, multiplied by e to the power of x, which is not the derivative, this is just the function itself. So I'm going to clean it up. E to the power of x times the ln of 2x minus 1 plus 2e to the power of x over 2x minus 1. And according to the textbook, that is 100% correct. Yes. So that's using the product rule, and obviously over there, that's just using that chain rule that I did show in the previous examples. Now the next example, B over here, it gives you y is equal to ln of x squared to the power of 3. Now, this one specifically, if you think about it, it's a function, in this case the ln of x squared, inside another function, which is that 3. Now, I told you guys, if you are able to use the log laws to simplify logarithms or ln, please do so first. So before I mess with the derivative, I'm just going to use log law 3, which is 2 times the ln of x. Because then instead of having an inside function, I actually have a constant function times the ln of x. Now you could have kept with that inside function, and I will show it to you over here, but this is just the easiest way to do it. And please people, remember, path of least resistance. Always paths of least resistance. So now I'm ready to get dy over dx. So using my chain rule over here, I first have to find the derivative of that to the power of 3. So I use 3 times 2 ln x to the power of 2. So that was the derivative of that outside to the power of 3 function. Now I have to multiply by the derivative of that. And lucky for me, this is just going to be 2 and the derivative of ln x. So that's just going to be 2 over x. So that's much easier than if you would have used the ln of x squared. Like I said, I'll show it to you just now if you want to see it. But yeah, this is the easiest way to do it. So I'm going to clean this up, and I'm going to say it's 6, because 3 times 2 is 6, 2 ln x squared over x. So that's it. Like I said, if you didn't decide to simplify into this, So if you just stuck to this top one, so you said y is equal to the ln of x squared to the power of 3. Then if you went straight for the derivative over here, I hope I have enough space for this, you would have gone first, the derivative of the outside function, which is 3 ln of x squared to the power of 2. Multiplied then by the derivative of the inside function. So because I've got the ln of x squared, that's again that function inside the logarithmic function. So that means we first have to find the derivative of x squared, which is 2x, divided by x squared. And by the way, if you look at this, you will notice x will divide into x squared, so you will actually end up with exactly the same result that you have over there. So you'll end up with exactly the same result as you have over there. So I didn't really need to do this, but hopefully you can see it's not going to be any different. Okay. Last example. Now, after I've done this example, I'm going to stop the video again because the video is going to get a little bit long. And then I'm going to give you one last video which will have past paper examples on these problems. So with this particular one, you should notice I again have the product rule. I have a function over here times another function. So dy over dx is equal to. So first we find the derivative of that first function. So it's that function multiplied by that particular function. So first we find the derivative of this function, which is going to be minus 1 over 3 x to the power of negative 2 times the ln of 4x plus 1. So according to the product rule, derivative of that function times that function plus. Now I have to find the derivative of this particular function, and hopefully by now you should be a little bit more comfortable with this. The moment there's a function inside that logarithmic function, I say the derivative of 4x plus 1 is 4 divided by 4x plus 1, multiplied then by that particular function, which is then a third x to the power of negative 1. So I'm just going to clean this up. So it's a third x to the power of negative 2 ln of 4x plus 1. And then over here I'm going to say it's plus. And I think what I will do is I will leave the 4 up top there. And then I'm going to move that x to the power of negative 1. You could have left it at the top, but I'm just going to move it down and make that exponent positive. I'll see what the textbook did just now. And the 3 obviously is in the denominator along with that 4x plus 1. So let's just check. In the textbook, they did exactly the same thing. They actually even went and they moved this one into this. They actually said it's minus 1 over 3x squared. And then they left that ln of 4x plus 1 over here, because obviously that doesn't have a negative exponent, so that belongs in that numerator, plus 4 over 3x times 4x plus 1. Now we've had a discussion about cleaning up these expressions, where I said instead of spending minutes that you really can't afford to waste on cleaning up the expression, a lot of the time you can just leave it like this. So if you do lose 1 mark because you didn't clean up the coefficients, they really don't have a problem with that. So normally you can actually just go and say, stop here. Especially in an exam or a test, stop there, leave the answer like that, and you should actually get most of your marks. So you don't really have to go and clean it all up. But this is just to make sure that this corresponds with the answer that I've got in the book, which it does. So in the next video, we will do a couple of past paper examples on this, the derivative of e to the power of x and ln of x.